Hi everybody, welcome to discussion number 6 of Socsci10, and today we're going to talk a little bit about Bayes' theorem. Now Bayes' theorem is used for question 8 on this homework, question 8 from the book, part of this homework. And you're going to run into Bayes' theorem pretty much everywhere in the sciences these days, and you can see it, has a lot of different forms, and it's incredibly useful for inferring what the probability is of some event happening from data that you've gathered. And you're just going to see it everywhere, and it's probably the most useful thing you can learn from probability and statistics is Bayes' theorem. So let's talk a little bit about it. So in this equation, in the upper left-hand part of the slide, you're going to see the probability of A given B. Now that vertical bar, that means given B. And so what that means really is we're saying, well, we have the probability A, right? That's what we're interested in. And we know from the data that B occurred. So given that B has occurred, what's the probability that A occurred, right? And you can see here it's labeled the probability of A being true given that B is true, okay? Now this is equivalent to the reverse, the probability of B given A, right? So Bayes is a great way of reversing the information you know. So if you know something about the data, you can kind of turn it around and ask a question about stuff you don't know about, right? So in this case, if we know what the probability of B is, and we know what the probability A is, and we know what the probability of B given A is, we can ask what the probability of A given B is. And so you can kind of invert what you know to learn something about the data that you don't know. Okay? Now, the top part of this equation, the probability of B given A times the probability A, right? If another way to think of it is this multiplication rule, which I've highlighted below with the red box, and you can see that that's really equivalent to this A intersect B situation. That's really what the numerator of the fraction, that's really what that is. It's the intersection of these two. And so another way that you can write Bayes' theorem is shown on the right hand side of the slide, is the numerator can just be A intersect B, right? That's what you're asking. You're asking for what is the A intersect B? And you can get that straight from this multiplication rule by applying the multiplication rule to the basic Bayes' theorem. But most often, though, you'll see Bayes' theorem described as in the upper left because it clearly shows the inversion. That reversing of the probability of one thing given another, that is the characteristic part of Bayes, and so that's why you'll see it in that form most often. Okay. But this is equivalent to really the intersection. Now, how do you want to understand this? The way to understand this is you look at our Venn diagram, and really what we're saying is we want to know what the probability of A is, okay? Given that we know B occurred. So if B occurred, we know the entire blue circle, all of B is true, right? So now A has a probability of being true, right? And we know that B is true, right? We know that B is true. That's really what we're saying is if we know that B is true, and we're really asking what is the ratio of the intersection to all of B, okay? That's really what we're asking here. And that's what you see in this form where you have A intersect B in the numerator divided by the probability of B, okay? So you would say something like, well, let's say the probability of B, the whole circle, probability of that being true is 50%. Let's say it's 50%. And let's say that the probability of A being true is also 50%. But we're really interested in how much did they overlap, right? How big is that overlap area in comparison to all of B? What is that going to tell us? If we can compute that ratio, that actually tells us the probability that A is going to be true given B is true. Because the intersection area, right, we know B is true. So the probability of that intersecting area, where the two circles overlap, the probability of that being true is 100%. Because we're assuming that B is true. right? We're given B. Now, if we don't know B is true, B is going to have some probability of being true, right? Let's say B has a 50% chance of being true. But in our situation, we just know B is true. We measured B, right? B is data. We measured it, we saw that it was true. We know that in general, maybe B has a 50% chance of being true. And I'm saying 50% chance just because it's just a number. Like if we don't measure it, we know it's a 50% chance of being true. So that's the probability of B on the denominator on the right-hand side. But we know, we measured it. We looked at the data. In the data, it says B is true. Okay, well, that's interesting. So that tells us something now. Because A and B overlap, they're not independent events, right? So if we know as B is true, then we know that intersecting area is true. But A itself may not be true. Now, the bigger part of A that intersected area takes up, that's going to increase the probability that A is true, right? So really what we're asking is we're saying, I looked in the data, I saw that B is true. Now if B is true, what's the probability of A being true, right? What's the probability of A being true? That's the intersected area divided by the whole probability of B. So let's take a look at another way to view this. In the book, when you're looking at question 8 in the book, you're going to click through to the relevant section. It's going to give you this formula up top. And this is in the context of a situation where you're looking at that denominator and you're saying, how is that denominator similar to this denominator here? We just have the probability of B. What's really going on there? What's really going on? Well, let's look at the top equation on the top left of this slide. In that equation, you see that what we're asking is what is the probability that T is true given D times the probability of D plus the probability that T is true given D complement. Now remember, D complement, and the complement rule is at the bottom, is 1 minus the probability of the other one, right? So if you know the probability A is 0.2, then the complement is going to be 0.8, right? It's going to be 1 minus that probability. And one way to view this is what we're really asking, what's really going on here is we are calculating on the denominator in the right-hand side of the top equation, we're calculating the probability of T. That's right. That's what that calculates. It's the probability of T. Now, the thing is, in this case, the argument is being made that T, all of T, is inside of D and D naught, which is another way of calling the complement of D. Okay? So it is a partition. And what we do is if we take the part of T in D and we add that to the part of T that's in D naught, right? We're going to get all of T. Okay? So we kind of divide T by where D turns into D naught, the complement. Now on the bottom we have a generalized view of this. So you see now that instead of just having two divisions, D and D naught, right, we can have as many partitions as we want. And we're going to sum them up, right? So in the image on the right, what we're really looking at is we have a whole bunch of events called B. And A is contained in all of these events, okay? Parts of A are contained in all these events. So in a way, we've partitioned the space of all possible events, okay? And what we're saying is we're interested in what's the probability that one of these events occurred, Bj. That's the probability that we're interested in. That's on the left-hand side on the bottom equation. What's the probability of Bj given A? So we know that A occurred, right? And we know that there's a piece of A in all of the partition pieces, okay? But what we need to do for that denominator, we have to sum up each part of A that is in that part of B, right? So we take this little, in B1, we take that corner, right? That little tiny part of A, take that part of A. And we're going to multiply that times the probability of B1. It's going to be small. but we're going to add those up using the summation, all right? And when we add all those pieces of A up, spread out across the partition of B's, when we do that, we're going to get the total probability of A, all right? In this previous slide, when we go back and we look at just the probability of B here, we're not really dividing the probability of A up across these B's. You can see that there's parts of A that are not contained in B, right? So we're just really looking at the probability of B here. But in this case, what we're saying is I'm interested in what's the probability of this partition happening, right? I guess one way to think about this is these partitions could be individual events that could be true. Now in the book they talk about whether or not you're sick or you're not sick given some medical test, right? So probability A could be the case where if it's true, you have a disease, right? But then when we look at these individual partitions, now it could be you have the probability of A, and B1 could be a test that you did, and that test could come out positive or negative. And so what we're saying is what's the probability that these things will occur individually? All right. And I think that what you want to do here is that denominator, you got to understand this denominator is a partition. And we can ask, what's the probability that any one of these situations occurred? Like probability of B2, what's the probability of B2 occurred given A? So if A is true, right, then we know that the probability of BJ occurring is going to be the reverse, right? So we know A is true. And we can calculate the probability of A given BJ, right? It's just going to be the probability of BJ being true, right? Which independent of A, right? Just the probability of BJ times the proportion of A that is in BJ, right? That is the A given BJ, and we can just look at that, and we know that A is true. Okay, so we know that that part of A is true, and so when we compute this ratio A given BJ times the probability J, that's the probability that component BJ is true. But we have divided this, we spread out the total weight of the B's, and so we have to sum up all those probabilities for the numerator. So these are all actually flavors of the Bayes theorem. And when you look at question 8 on homework, you're going to be asking yourself, you're going to be asked, what's the probability that you have a disease given that the test came back true or the test came back false, right? So if we know the test came back true, so in the top equation here, T will be the test. Probability the test is true. What's the probability you have the disease? Well, probability you have the disease is the probability that you have the disease in general, independent. Maybe 5% of the population has the disease, right? That's going to be probability of D. And then the probability of D prime is going to be the complement of that. So it's going to be 1 minus 5%. It's going to be 95%, right? And so if you're looking at that numerator at the top equation, you say the probability of D is 5%. So the probability to have the disease is 5% in the general population. And you know that the test is a certain percentage accurate. It's 95% accurate if you have the disease. So then we have the probability of T, the test becoming true, given that we know you have the disease, times the prevalence of the disease. That's the first part. So we did this partition. We partitioned space into people who have the disease and people who don't have the disease, right? And now we're asking, what's the probability that you have the disease? This is just the same as the bottom equation, except that instead of which is the bottom equation is a generalization of this idea, where you can have many B events, right? But in the top equation, we just have 2. D, you have the disease, or you don't have the disease, right? So what we're really asking is, what's the probability the test is true? The test says, so we know we took the test and we know it's positive. So what's the probability that that you have the disease? you have to have this denominator that looks at that case where the test is true if you have the disease. So how accurate is the test? But sometimes the tests are wrong. You get a false positive. Well, how often does it say you have the disease when you don't? That's the second part, where we're looking at the complement of D. So there's a certain number of people who don't have the disease. It's the prevalence of people who don't have the disease, right? We partition the space of people, two groups, those who have the disease and those who doesn't. That we can call them B1 and B2, for example. But in this case, because there are only two possibilities, you either have the disease or you don't, it's just a binary partition, right? We don't have many different cases. But it can be generalized, as I mentioned before, with the lower equation. And then we have to look at, well, what's the false positive rate? What's the probability that test is going to say that we have a disease when we don't, right? That's the false positive rate, times the prevalence of not having the disease. And you add those together, that gives you that denominator. And we know that you can see that the numerator actually shows up in the denominator too, right? Why is that? That's because the denominator is really this partition of probabilities across the space, right? And what we're asking is, we're asking in each of these cases, right? For a particular case, what's the probability that this is the case? So you've got to sum up all of the probabilities of all the cases and then compute the ratio, right, of one particular case, the numerator's case, of happening out of the sum out of all the cases. So the numerator, it will show up in the denominator, in the summation of the denominator, okay? It will show up there. And in these general cases where you have a partition. But you're asking, well, what is that case? And this is a way, really, because we only know that we did the test and the test came back true. So then what's the probability we have the disease? We have to look at the situation where we have the disease and when we don't. And we have to look at the situation where we have the disease and the test says we have the disease. And we have to look at the situation where we don't have the disease, but the test says we have the disease anyways, right? That's the partition of the space of the population in two groups. And then what we're interested in is we're interested in a situation where we have the disease and the test says we have the disease, right? And so that is how you compute that ratio. Now, this is an amazing result. One of the things that you have to keep in mind, though, about this result is when you have this partition, these partitions can't overlap, right? B1 and B2, they don't overlap at all, right? So otherwise, if you had an overlap, you would count some part of the space twice when you summed them up, right? But if this is a partition where there's no overlap, and you can sum all the B's up so that the total probability of all the B's is 1, and you're really looking at the probability of A given each individual B, right, times the probability of that individual B, and you sum those up, and that's going to give you your denominator. And then you can ask, well, what's the probability of one of those situations happening? And you can use this inversion to ask that question, because the values on the right-hand side of these equal signs, you can compute from the data, from what you've measured about the data, right? From what you've measured. You know, in the case of the book, you know that how many people have the disease in the population, you know how accurate the test is, and you know what chance the test could tell you have the disease and you not have it. That would be the false positive rate, right? You know these things about the test. Those are properties about the test, and you know the properties of the population, right? You know how accurate the test is, what's the chance of getting a false positive, and how accurate the test is. And you also know how many people in the population have the disease. But what you don't know is, if I test an individual in the population and the test comes back positive, do they have the disease? It could be a false positive, right? They might not have the disease. Might be the case that it's a false positive. So how do you know? Well, you can use what you know about the situation, about the prevalence of disease in the population, and about the accuracy of the test to compute that probability. And this is incredibly valuable in science, in the social sciences, a lot of research at UCI, at the graduate level, and in many psychology and cognitive science programs around the world rely heavily on techniques based on Bayes' theorem. And it could be the most important thing that you learn in this class if you go on to a higher level where you are learning more about probability and how to apply that to derive insights about stuff that you can measure, insights you can't measure about stuff from stuff that you can. Okay, and by doing a test, right? I take the test, I get a result back, says you have the disease. How accurate is that? Is that true? What's the probability of him really having that disease or her really having that disease, given the test? I mean, the tests are not perfect, but we know how many people in the population in general have this disease. So you have these things you can measure, and you can infer. It's the technique of inference. You can infer how accurate, how good that result is. And what you will do is, how can you use that? Well, you can use that because if you do that and the probability that they have the disease is low, right? You can say, oh, well, we did the test. It says you have the disease, but maybe there's a high false positive rate, or maybe the test isn't very accurate, and so it doesn't really pick up that you have the disease well. So you can calculate this probability. If it's too low, you can say, well, let's do another test. You can do the test twice, right? Because then you're combining the results of each of these tests, and that will increase the accuracy, right? So if you ran this test twice and it came back positive both times, well, the chances of it you're increasing the probability that you're right. So you can use this to figure out how many times you want to you should run a test, so you have a high degree of confidence in whether or not you're really determining whether or not someone has this disease. It's an incredibly useful technique. Learn the Bayes theorem. It can come in different forms. This is the partition form of the state space, right? It can be multiple states, or it could just be two. One state and a complement. Another way to view it is this intersection of two probabilities using the multiplication rule, right? And the classic explanation in the left-hand side, if you understand the inversion of the probability of one thing given another, can be computed from the reverse of that. And you can get that reverse from your data. Then you can immediately make this inference using Bayes' rule to reverse those two parts, right? Swap A and B, because you can compute B from A, but you want to know A from B. Well, you can use Bayes' rule to do it, and it is a classic inference technique, and it's incredibly useful. Good luck on the homework. I saw that it is due on the 10th. That's tomorrow night, and I'll see you guys next week. Good luck.